So here's the plan of what I want to talk about today. Number one, we'll talk about me, tell you my background. I'll give you my view on what is math, because that might be different than yours, and that could be the starting point of bigger differences. But the short answer to that is, to a professional mathematician, I think the most common answer, and we argue, is that math is the study of patterns. It's the science of patterns, studying them, understanding them. I'll elaborate on that. Item three is that I'll talk about what are the goals of education. And again, we have different answers perhaps, but my view is that education should help people it should teach people to think like a mathematician. Mathematicians have a different way of thinking about things, and getting people to understand that, to be able to do it, is what I would say was a successful math education, in my view, in terms of how I see people coming into universities. I'll give you some thoughts on what I see as the state of K through 12 math education, and some ideas, some golden nuggets that I've thought of that may be totally worthless or may be useful to think about as how education might be incrementally changed in various ways. And along the way, I'll probably point to a bunch of items on the table up here. I've brought some physical things. I tend to be a hands-on mathematician. I'm a sculptor, and I tend to make things that I feel have some mathematical thinking inside of them. Okay, so let's start at the top. Item one, talk about me. This is me. I'm also showing my wife, Elizabeth Heathfield, partly because a lot of what I'm going to say actually comes from collaborations. We've done a lot of work together. She's a teacher, has been a teacher in the school district, and we spent a lot of time visiting many schools, trying out different kinds of activities, and writing lesson plans and articulating ideas together. So much of what I'm going to say is really Elizabeth's ideas. But let's talk about me. So I'm a retired university professor. So I've had a lot of experience teaching math courses at the university level, not in math departments, but in computer science and electrical engineering departments, where there's a lot of math, and I would teach the most mathy courses in those subjects because I enjoy that. I think I'm good at that as university professors go. I have no experience, though, teaching in a regular K through 12 classroom. I don't think I'm at all good at that. So I just want to qualify everything I'm saying here, that I've never spent like a whole day with the same students having to deal with all the things that come up in class. I pop in, I do some fun activity, I get everyone excited, everyone says, wow, that was really fun, and then I go away, get to go home and have fun, where the teacher has to stay there with all the other issues. So I'm not a teacher. I'm also not an education researcher. So there are many professional people who approach the question of how do you improve education scientifically, empirically. They'll say, oh, let's try changing this little thing in a classroom, and they'll do an experiment where maybe you go into a school and you randomly pick half the classes and they try the new thing, and then at the end of the year you give everyone a test, and if the ones who tried the new thing are 3 points higher at long division than the other ones, then you say this is a good thing. It's a scientific methodology to approach how to make education better. Anyway, I don't do that. I don't know anything about that. But I hope that some of these ideas could inspire people who can do that to say, oh, well, let's try that and see if it actually works the way George thinks. So what do I know about public school education? I went to public schools in New York, really good ones. I learned math well. I came out to love it. I think I had great teachers. I also had very math literate parents, and they always were thinking mathematically, and I think encouraging me in little ways at home, and I think that's also a big part of what worked for me. What I do now mostly is create geometric sculpture. I make mathematical things. I'll show you pictures of it. And I do informal math education in various ways. So let me elaborate on that. What do I mean by informal math education? I mean not spending all day in the classroom following a curriculum. I work with teachers, I talk to teachers, I visit classrooms, and I do things in there. I've developed lesson plans after Elizabeth taught me what a lesson plan looks like. I've done a lot of professional development for teachers, working with a bunch of teachers to get them more excited, to keep them excited about math, to help them understand what university people think the people coming through the K through 12 pipeline should know by the time they graduate. Another thing I've done is I spent about 5 years creating the Museum of Mathematics in New York City. That's a large institution for informal math education. Families can go there, they can do various things. I won't make that part of my talk today, but it's something that if you raise $25 million and you build a big thing, you can have a great spot for people locally to come, but it doesn't scale to the rest of the country, the rest of the world. So it has a certain place, but the things I want to talk about today, I think are scalable. They can be put in classrooms everywhere. The other thing I do is I create sculptures and often go somewhere, work with people to assemble it. So the community will help me build the sculpture and it stays there. And the sculptures have mathematical stories behind them, and I hope that that serves as a kind of inspiration for people to say math is cool, math is enabling to make things. I'd like to figure out how that works, to start asking questions, etc. So that's a kind of informal mathematics. All right, so I'll just show you some sculptures. I'm not going to spend a lot of time, but if I wanted to give you a talk on the mathematics of sculpture, I would tell you all about the patterns in here and the pentagons and the colors. That's not today's talk, but I just want you to have a feeling that I'm using math in here. I could not build this without kind of a deep knowledge of linear algebra that I'm using to calculate planes and angles, and there's geometric ideas, there's topics from polyhedral stellation theory. Anyway, there's a lot of underlying math which comes together to make these pieces exactly fit and to have the feeling that I want. I'd like to work in different materials. So this is wood. It's actually built over, first I made a fiberglass sphere, and then it's like a mosaic glued over that. This is 3D printed. I think I have one 3D printed item with me. See if I can hold this up. And maybe there's enough light that you can see this. But probably at the end of my talk, you should come and come look at all these things. But 3D printing is an enabling technology that can build very complex geometries, things that you may not be able to cut out the pieces and build in your shop or whatever. The 3D printer can. And it's important to understand what it's good for, how you can use it. I think there are great ways you can use it in a classroom. I'll come back and talk about technologies. It's one of these technologies that some people have hyped. We need one in every classroom, and if you just teach 3D printing, that'll solve all of education's problems. It's not that, but it does have certain strengths. I like to work with paper. I've always worked with paper since being a child. You may think of paper as something just for children, but you can make very complex, very intricate things, and paper is just a lovely medium and very easy to experiment and revise at low cost. Then when you have a design you like, you can work up to, say, cardboard or wood or metal and some sequence. This is cardboard. Nicely donated by a local company that prints packages that has scrap cardboard. And if you can get scrap pieces of cardboard, you can make really big, cool things. This is also built with an enabling technology of a laser cutter. So the shape is a polar zonahedron, and the pieces are held together with little black binder clips. And you can calculate the pieces, design them on a computer, have the laser cutter cut them out, and then snap them together. I'll show some activities like this in a few minutes. But again, it's a way that you can use technology to do new things and incorporate that in ideas of how do you bring that into a classroom, how to use that for education. This particular shape, the polar zonahedron, is one of my favorites. So what you're seeing here is actually the little library that Joan had mentioned in front of our house. You can open that up, take a book, leave a book. It's a 10-fold polar zonahedron. I would be very happy to talk all day about that structure. It's a beautiful structure. People just don't know enough about polar zonahedra in our culture for some reason. Luckily, I've made a video about that. So many of the things that I'm talking about, there are further explanations on my website, georgehart.com. And there is a YouTube video you'll find about a little polar zonahedral library, if that's your interest coming out of here. I like to work with plexiglass sometimes. It's an interesting medium. This is based on an Icosi dodecahedron. It's a spherical sculpture about this big. Each piece had to be formed and heated in the oven, softened up, and put in a jig so it would cool with the correct twist in it. Acrylic plastic is not flexible, so everything had to be very accurate to exactly fit without gaps. That kind of technical challenge I enjoy. I like the engineering problems of how do you design things. And this, like many of my sculptures, what you're seeing is a final result. Behind that was all kinds of jigs and forms and templates and things that you no longer see that were actually much more work to create. How do you build a structure to hold this all together that comes out through the holes kind of thing? That are part of the fun for me, part of what makes it an interesting engineering challenge. This is a large sculpture, Michigan University, Albion College. It's 9 orbs, each a little over 1 meter in diameter, each one slightly different, put together by a whole bunch of people, a whole bunch of students and faculty in the community. Over a period of a day, we assembled it, and I'll show some examples of things like that. So to summarize the section 1 about me, basically I love math. I hope you can see that there's some passion there that comes out in the form of making mathematical things. And I just want to share that joy. I mean, math is to me the best subject. I'm sure you can have a historian come up here and tell you history is the best subject and whatever else, but they're wrong. Math is the best subject. Math is everywhere. Math underlies things. It lets you see things deeply. It enables you to do things you couldn't otherwise do. And I just want to kind of share that with the whole world. I wish everyone could love math the way I do. And then there's a second reason for doing all these things, I think. If you think about it, of all the things I could do to try and make the world better, teaching people to think about math, to me, seems like the most socially responsible. It teaches you critical thinking. Mathematics, as I'm going to try to explain, builds up logically from one statement to another, following a logical pattern. If you're used to thinking that way as a child, if you understand how one thing has to be true because this other thing is true, and how that builds up a kind of a mental structure that can be very complex, then you're thinking like a mathematician. And that kind of thinking then just leads to kind of a rationality, a kind of a critical thinking, a cultural awareness of what's happening that I think is a skill in everything. And hopefully over generations, if we can increase the amount of critical thinking with each generation, the world will get better and better and be a wonderful place. So anyway, that's me. Item 2 on the agenda, I'm just going to check my watch every now and then. Oh, good. Item 2 is what is math. So you probably have some notion of what is math. But I'm going to interrupt and just do a little activity here first before telling you what I think math is, because it's possible that your answer and my answer are different. So let's see if I could show you a little video, and then I'll do a little demonstration of the kinds of things that I think is math. And somewhere here is a video. It's all of 1 minute.
Okay, I'm going to show you how we take this bagel and cut it into 2 parts that are linked together like a chain. I'm going to cut in at the end here, and then cut to vertically over here, and then down to horizontally on the inside here, and do that same cut 4 times, just rotating 180 degrees in between each cut. So we start horizontally and cut vertically, and then down to the inside, rotate 180, start at the same spot, cut vertically, and then horizontally down to the bottom, turn 180 degrees again, cut in vertically, and to horizontally inside, and one more 180 degree cut, vertically. It's a little soft in here. There. Now we just have to tease it apart gently, and it'll separate into 2 pieces. And there we have it. 2 equal linked parts.
All right. So to me, that's math. I thought I would perhaps give you all a bagel, but that seemed like too much and a knife. I have done this as a workshop, but it takes a while. But I thought I would be brave and just see if I can demonstrate. People say to me, is that really true? Is that fake? Anyway, it's true, and you can do it. And I may or may not be able to do it here. I'm hoping that if I do this here, the camera over there will pick this up, and then you'll see the fingers falling to the floor as I cut them. A few magic buttons there. Okay, so you can do this at home. I have this video online. You can find that. Look up Mathematically Correct Breakfast. You start at the top. Oh, I have to stand over here. This may not work because I'm a righty and it's once a lefty, but so far so good. That's the basic cut. You go in at the top, you come around to the front, and then you go in the inside of the bottom. And you just do that 4 times. There's a symmetry. So I rotate it about this line, and I come here and do it again. It's much easier on a table than on a vertical, whatever that is. Then I'm going to flip it this way and go in at the opposite point and cut. And in theory, this matches up in the middle, but my cutting isn't that accurate. And then the 4th cut, again in the top, coming out here. And so it may be clear that there's like some geometry in here. That to me is part of the math. Then if my knife exactly met, oh, that came out well. Okay, so can you see? Am I on camera here? Yes. So there are 2 pieces. They're actually congruent. They're exactly the same shape. The video goes on to ask the question of, so now what's the surface area? You know, the regular plain cut gives you a certain amount of cream cheese. This is a little extra. With a little bit of calculus, you can calculate how much bonus cream cheese you get as your reward. So this is just one of many different interesting ways you can cut a bagel. I'll put that there. I have a couple of other videos on how to cut a bagel so it's tied in a knot. I have a bracelet I can show you later, which is tied in a knot that started out as a loop and was cut in a certain way. It relates to some activities you may have seen with a Mobius strip. You take a strip of paper, and if you close it into a cylinder and cut it in half, depending on how many times you twist it, you get different results. I just made, in a sense, a 2-twist Mobius strip out of the bagel, or I treated it as if it was one and cut along the same line that your scissor would cut if you went down the middle of that. This relates to a branch of mathematics called topology, which is a sort of a generalization of geometry. Typically, you don't see this until like you're at the university level in math, if you're a math major. But it's totally accessible at the beginning stages to younger people. And if you were a math teacher trying to think of math enrichments, you might not look up, bagel cutting online to find out what math videos are out there. But I come at it from the other end. I think of what's some cool math that I wish more people knew about and make a little video about it, a little activity about it. So all the things I'm going to show you are sort of like that they're not something you need in order to teach the standard curriculum, but I hope they help people think more about mathematics. Let's see if we can get back to where we were. Okay, so I was in the middle of showing you that. There we have cream cheese. There's some interesting toasting problems, by the way. How do you toast it? But okay, so we were on item 2, what is math? And this is what could be perhaps a popular view of what math is. It's maybe a high school senior, if you said to them, what is math? They would say, well, all these things I've gone through in school that were called math class. And you can break them down differently and pull out some parts to emphasize. But you start the young grades with counting, and then you understand some arithmetic things like adding and multiplying and how to deal with base 10 multi-digit things. You do some algebra. You learn about polynomials and geometry, trigonometry, sines and cosines. There's a lot of miscellaneous things in pre-calculus. Limits and series and logarithms and exponentials. And that's sort of what people see before going on, say, into university. This is a really arbitrary set from the mathematician's perspective. It makes a lot of sense for a reason, but if this is what you might see as math, I would contrast that with this is sort of what I see as math. At least this is something that I just pulled up online. It's one mathematician's kind of mind map of different fields of mathematics. I would actually disagree with some of the sizes and relations and things. But the general point is that math is a very rich subject with many, many different aspects that interconnect. And there's many beautiful things. And some of the things that are emphasized here are not things that you might think of as math, maybe things you've never heard of. Somewhere buried, let's see, does my mouse come through on the screen there? Yeah. Somewhere buried, I was able to find arithmetic. So we do have some arithmetic, and the kind of algebra you teach in school is called, we'll just call this pre-calculus algebra. Mathematicians use the word algebra for something totally different called abstract algebra here. There's some trigonometry, and oops, let me go back. And you may see complex numbers in high school. I keep clicking. Anyway, this is a rich set of things, and mathematicians are very interested in the relations, the patterns, how you study one thing and parts of that are used to prove things in another field, and how they connect, and how one field is like another field, but you've changed terminology or whatever. It's a very rich set of things, and from all this, we've selected this particular path. It's just like whatever this is, a half dozen dots that connect to teach in K through 12. If I just came at education completely from scratch as a mathematician, there'd be a question of like, well, which things should I teach and why? And the choice is good, but to a mathematician, the math is the study of patterns, all different sorts of patterns. And some kinds of patterns are in that standard K through 12 course. The most important thing to a mathematician is when you study patterns, you want to understand them in some sense, not just to see them, but how one implies another, how they relate to each other, what's the logic? How do I prove this thing based on this simpler thing? How is that proved based on some other simpler thing, etc.? And where does this all stop at the beginning? We're looking for explanations. We're looking for a logical connection between things. So elementary school patterns, for example, counting. We have numbers, 0, 1, 2, 3, 4, 5, etc. By the way, I start with 0. It's really, I think, important to start with 0. You might think counting starts with 1, 1, 2, 3, 4, 5. When you think more generally about mathematics, I'll just tell you, it saves you a lot of time and trouble. Start with 0. That's where counting begins. When you count, every time you take a thing, you say the next number, 1, 2, 3, 4, 5. When you run out of things, whatever number you said last is how many things there are. That's the essence of counting. Well, if there are no things, the last number you said would have been 0, and that's how many you have. So you should start by first saying 0. How many things do I have? 0, then 1, 2, 3. Because it's cleaner, everything is nicer if you begin with 0. Second line there has a pattern that you might think of multiples of 7, 7, 14, 21, a different, more advanced pattern. The third one's a more interesting pattern. It's called the Fibonacci numbers. Each number, we start with 0 and 1, and then from there on, each number is the sum of the two previous numbers. If you keep doing that, it grows and grows in an exponential way. It's interesting to understand how it grows and why. It's a pattern that shows up in plants and many other things. The bottom one is a pattern of prime numbers. Again, many questions, many interesting, subtle things that mathematicians can't even answer. Are there an infinite number of twin primes, etc., about that set of numbers, but you can understand the questions at a younger age. So these are patterns in numbers. When these come up in class, what I would encourage as a mathematician is to always get the students thinking about why. How do I know things about these things? Let me start with something as simple as the kind of pattern you observe that addition is commutative. If I add 3 plus 7, I get the same answer as 7 plus 3. Students will notice that after a while, but can you explain it? Why is it that 3 plus 7 is 7 plus 3? You could do 50 examples, but how do you know if you did, a million plus 7 is the same as a 7 plus a million? That's an example that's too big to count. What's the reason to believe that? Because later in algebra and trigonometry and other things, you're going to explain things based on simpler things. So how do we explain that addition is commutative, as we'd say there? What a teacher might do is something like this, to draw a picture and say, well, what do we mean by adding? We mean if we put 3 things in a row and then 7 more things in a row and count them, we'd have 10. But on the right, I put 7 things and then 3 things. How do I know that's the same? I can count them in this example, but how do you know it's always going to be the same? And an answer that a teacher could give that a student would appreciate is that if I make that picture on the left that represents 3 plus 7, and if I walked around to the other side and looked at it, then I would see the yellow on the left and the blue on the right. I'd see exactly the picture that's on the right. So the picture of 3 plus 7, if I just walk around and see it from the other side, is the same as the picture of 7 plus 3. And you can imagine doing that with any possible number. So that's the kind of an explanation that addition is commutative. It's a way to visually think about it. It's not how mathematicians explain it. It took mathematicians centuries to explain why addition is commutative. I won't give you the answer, but around 1900 or so, different mathematicians came up with very long, complex explanations. Okay? The first proof that 1 plus 1 is 2, a rigorous proof that mathematicians accept, is like 500 pages long, believe it or not. So to a mathematician, that's interesting. This is not a proof because when you walk around the other side and look at it and you imagine doing that, you're actually using a lot of information about space and rectangles and symmetry. Mathematicians want to prove things only using simpler things. So you can't use anything about rectangles or space or geometry. You have to have something simpler than addition to explain it. And coming up with something rigorous that satisfies that is a whole nother lecture. That's a university topic. But the idea that you should find an explanation, a reason to believe it, is something that we can do at this level. So that's my answer to that. If you wanted to say, why is multiplication commutative? Why is it that 3 times 7 is the same as 7 times 3? That picture doesn't work now. What does this really mean? If 3 times 7 means I add up 3 7s, I have that picture of, say, a bar of 21 things. On the right, I'm adding up 7 3s. I have that picture again of 21 things. But the question is, how do you know that's always going to work? You could do a bunch of examples, but why do you know that no matter what 2 numbers you pick, x times y is going to be the same as y times x? It's something that we're so familiar with, having done it. It's hard to step back and try and see on what basis could you prove something like that. Again, there's a nice answer. I think when I was growing up, and maybe many of you are growing up, no one tried to explain this. This is just something you would see, and the teacher would say, oh, well, whenever 2 numbers you take, a times b equals b times a, that's the law of that multiplication is commutative. Mathematicians want to say, but why? How do I know that's for sure? Even on big numbers that no one's ever multiplied. And here's a nice way to explain that, and I understand that this is often taught nowadays in classes, that what do I mean by 7 plus 7 plus 7? Well, I could put them together and make that kind of egg carton shape on the left, which is 7 3s. And what do I mean by 3 plus 3 plus 3 plus 3, 7 of those? Well, that's that egg carton shape on the right. And how do you know that they have the same number of things? Well, you can just walk around to the side. If I look at the egg carton on the left from the side, it'll look like the egg carton on the right. So it's the same picture. The picture of 3 times 7, when seen differently, is the picture of 7 times 3. Again, a mathematician wouldn't accept that, but I think to a child, it is a very good reason, way to understand it. And more, it sets the pattern of looking for explanations, looking that if the teacher tells you something, you should say, but why is that true? A good exercise is that a teacher might give a false lesson and say, I want you to tell me what's wrong with this. And the students should be able to be critical and think of what's wrong with it and explain something if it's true or why something is not true, always looking for explanation. But this is one pattern I thought I should talk a little bit about because this is at the core of a problem that I see at the university level when people come in through high school that they haven't fully understood what I want to show you here. This is a doubling pattern. So if you started with that 1 in there, you could imagine doubling it to get 2, double that 4, 8, 16, 32. You can continue it forever. I just showed a finite amount, but 64, 128. If you go to the left, every time you step left, you're cutting in half. So to the left of 1, we'd have a half, a quarter, an eighth, etc. Common pattern. I can remember, sitting as a child doing this pattern in my head, to however many digits I could add up in my head, up into the thousands, and having this amazing realization that numbers go on forever from thinking about this particular pattern. But what I want to show you is that I can connect that pattern to this other pattern, this counting pattern. So part of what mathematicians do after thinking about patterns is think about patterns that relate other patterns. So what I want to claim is that these two patterns are really the same pattern. How can they be the same pattern? The top one is counting, the bottom one is doubling. But if I think of numbers on the top and think of addition, what I can find there is exactly the same as thinking about numbers on the bottom and multiplication. Let me show you what I mean. I might, for example, if you could see my arrow there, I might say add 1 plus 2 and come up with 3. I'm using addition up here on 1 and 2, and I'll get 3. That same movement of this arrow, if I came down here, if I took 2 and 4 and multiplied them, I'll get 8. The product of 2 and 4 is 8. So what I did with addition upstairs, I'll do with multiplication downstairs. So for example, if I take 2 plus 3, I come over here to 5. If I come downstairs, if I take 4 and 8 and multiply them, the answer I get is 32, which connects up here with the 5. And anything that I want to do upstairs with addition corresponds to something downstairs with multiplication. 0 is the identity element. If I add, say, 0 and 3, I get 3 again. Down here, 1 is the identity element. If I multiply 1 and 8, I get 8 again. I can add 0 to anything, get the same thing. I can multiply 1 by anything, get the same thing. So what a mathematician would say is that these two patterns are isomorphic. By that, what they mean is that they're really the same pattern. Anything that you know about addition with the upstairs numbers translates to an equally true statement downstairs about multiplication and the downstairs numbers. This is the most important pattern between patterns that people could understand at the high school level. It has a fancy name. It's called taking the logarithm when you go upstairs and taking the exponential when you go downstairs. When people learn this in school, they often see it in little pieces and they don't realize what this big picture is, what the isomorphism is between these things that they know. But it's enormously powerful. In higher level courses, you'll do hard problems all the time. So for example, upstairs, if I double, like take 2 and double it to 4, that corresponds downstairs, instead of adding with itself, doubling, I'll be multiplying by myself. So downstairs, when I double, if I go from 4, I get to 16 by multiplying. That means halving upstairs corresponds to square roots downstairs. If I want to take a square root of the square root of 16, and if square roots are like hard, I can just go upstairs, say, but I can do halving, that's easy. Take half of 4, that's 2. Then to get my final answer, go back downstairs and say the square root of 16 is 4. There's many hard problems that involve things like square roots that turn into easy problems by taking logarithms. This is a source of enormous confusion with students, that they've memorized certain sentences. The log of 1 over x is minus the log of x, whatever. They don't understand that that just corresponds to a simple symmetry in this picture. Anyway, patterns between patterns, such as this, isomorphisms, is a big part of mathematics. So to summarize this section of what is mathematics, I'd say the content of mathematics is about patterns and structures, understanding them, explaining them with logic, trying to be clear about the reason why one thing relates to another thing. A very big part of math is also this interplay between visualization and notation. The word log base 2 of x or something may be confusing, whereas that picture of just lining up things might be clearer. Being able to understand what that notation really means in terms of visualizing. Or something as simple as like a circle is the set of points equal distance from a given point. The center is a visual idea of a circle. X squared plus y squared equals r squared is a formulaic, algebraic expression of a circle. Seeing that they're the same, being able to translate from one to the other and solve a problem in whichever domain makes it simpler is part of math, that interplay. And underlying all this is beauty and creativity. Mathematicians love beauty. Mathematicians will tell you about a theorem is just so beautiful or a proof is just so elegant. There's an aesthetic to mathematics. Understanding that is something that could be brought out all through math education. In terms of the process of doing math, teachers say math is not a spectator sport. You don't learn math just by watching someone write something on the blackboard. You have to actually do it to internalize it. Math is about finding these patterns, looking for them, and then finding a justification, explaining them. That's sort of a puzzle. Until you have the answer, you have to work on, well, how does this work? I can't quite see the pattern, how to extend it, or why it's true. You have to be comfortable solving hard puzzles and being in this mental state of frustration, or I can't solve it. And then eventually, hopefully, you have this aha where you figure something out and it sticks with you, just becomes important. And what professional mathematicians do, and researchers that are using math in their research, they're working on hard problems. They're trying to solve, how do you cure a disease, or what's the structure of this protein, or whatever. They're using math, and they're struggling with puzzles. They don't know the answer. And getting students comfortable with that state of not knowing the answer is a very important part of learning to think like a mathematician. Okay, I figured I would have been talking a whole lot at this stage, which is correct, so that I might show you a quick video, or at least part of a video, again, illustrating the kinds of things that I think help mathematical thinking. This is one of a series of videos I've made for the Simons Foundation, and just watch.
Can a curved surface in 3 dimensions be made entirely of straight lines? Well, yes. A cylinder is a curved surface, and there's a straight line through every point. But a cylinder is straight in one direction, so it's easy to see its lines. Can a doubly curved surface, like a saddle, be made of straight lines? Surprisingly, yes. Just twist these discs to tilt the connecting strings. You find that between the 2 extremes of a cylinder and a double cone, there's a continuous range of surfaces like an hourglass, called hyperboloids, and they're entirely made of straight lines. In fact, for any amount of turn in one direction, you could also turn the same amount in the other direction to make the same hyperboloid. This means the surface has 2 straight lines through every point. It's a beautiful form. Can you imagine making one large enough to walk through? We'll warm up by using shish kebab skewers for our lines and small ponytail rubber bands to join them. It's wonderful how an initially disorganized mess begins to structure itself into such a natural form. Because the crossings are movable, the final result is dynamic. It flexes beautifully, should you want that. But let's try a different trick. You can compress it from the sides to change the circular cross-section into an elliptical form. The sticks tilt, but stay straight. That's because if you stretch or compress uniformly in one direction, you map circles into ellipses, but lines remain lines. So the resulting elliptic hyperboloid is still made of straight lines, though it's more interesting visually. Our plan is to proportion it and sink it into the ground to make an arborway for people to walk through. We'll practice with some scrap bamboo to get a sense of the engineering challenges at full scale. Flexing this model is fun, but we see we'll want to brace our structure so it doesn't flex. For the full-scale version, we first decide how many lines we want. We're placing 24 pieces of 12-foot-long bamboo in each direction, making 2 families of diagonals. This gets rolled up into a cylinder, taking care that one set of diagonals stays on the inside and the other set stays on the outside. Everything connects with heavy-duty rubber bands designed for outdoor use in agricultural applications. Then the structure is stretched and compressed from a circular shape into the elliptical form. Because the sticks now have different slopes, the heights of their tops now vary. So we need to saw off the ends of the longer ones to match the height of the shortest ones. Then we add a ring around each end using pliable pieces that can curve to the shape of the ellipse. This is the bracing that prevents flexing. The plan is to rotate it so it's oriented on its side and people can walk through it. Digging the trench for it to sit in is the hardest part of the job, but when it's installed, it looks great. The result is a unique garden arborway, a triumphant arch that reminds everyone of the beauty of mathematics and how certain curved surfaces are actually composed of straight lines.
All right, so that's what I consider math or math education. That hyperboloid is at, there's a teaching garden at UBC in Vancouver, and they had invited me to think of something mathematical they could do in the garden and to create there, so that's what I came up with. But the idea is that by building that, in the process, you have all kinds of opportunity to have informal discussions about the math, what's going on, and then when it stays there as an object for people to come and look at and walk through, again, it raises mathematical questions. It's just a teaching opportunity to talk about it. So that's my idea of what math is. Let's see if I can get back. Oops, back to here. Okay, so talked about what math is. The question is, what's the goal of math education? Well, this section is really just one line. I think the goal of math education is to have students learn how to think like a mathematician. That's the goal. It's not that you have to memorize this multiplication table or be able to do long division or anything. It's to be able to think like a mathematician. So everything that I said previously about what math is, that's the details of what exactly should you be able to think about. You should think about patterns. You should think about explanation. You should be able to think visually and relate that to formalizations. You should see the beauty. You should be able to engage in the process of searching and justifying things. Being able to do that is to be able to think like a mathematician. These are the skills that you need as you get to the highest grades and you get to the university level. When students come in to courses that I teach at the university level, and we start to teach things like proof by mathematical induction, this is a topic where there isn't a step-by-step cookbook. It's not like adding numbers where you say add this digit, and if it's greater than 10, put a 1 here, and this and that. There's a formula for how you do elementary mathematics. That's why we're able to teach it. At the university level, it's like, well, think of how you're going to solve it. There isn't a formula. There's an ability to recognize when you have solved it, but there's a step in between where you have to be creative and try a lot of things, and many fail until you do solve it. Getting people comfortable so that they're ready for that sort of university level work is part of thinking like a mathematician. It's what all these things enable. Okay, so that was item 3. That was fast. Item 4, the state of math education. So I've gone and visited all these schools. I've done lots of workshops. I've designed activities like what I've showed you. I've done them. I've written them up and gotten feedback. What's my sense of the current state of education, talking K through 12? So first, let me just give a little footnote there that I'm not talking about test scores or anything else. Many people will tell you the state of math education can be judged by looking at, the PISA scores and how 1 point changed on this or that. I don't think test scores test for the things that are important. Tests are convenient because it does correlate to some extent with mathematical thinking, but no test is really the same as like sitting down with someone and saying, let's work on this, and talking and understanding how they think. People need some kind of evaluation for social reasons, so tests have become important in some minds. Instead, I look at it as a university teacher, what can students do and not do, and just based on all my different classroom visits, my interpretation. So everything from here on is very subjective, and feel free, we'll have a discussion time later. Okay, so the summary answer is that it's mixed. There are some wonderful teachers doing wonderful things. There are teachers who really understand math the way I do, and they're able to communicate that to their students and explain things. And there are many teachers also with math anxieties, teachers who don't really know how to think the way a mathematician thinks. That's my giving them a grade of what I observe. And it's not their fault. They weren't taught. They didn't go through a math program. So what's the solution to all this? Teachers need training, they need support. It's a huge problem. I offer little things that I'll talk about. But basically, there's great things happening, and there's also situations where, of course, the students aren't going to learn math because the teacher doesn't know how to think like a mathematician. This is my view kind of from inside the classroom. From outside the classroom, what's happening? Teachers are fighting against aspects of our culture. There are these attitudes that math is hard and therefore I can't do math. The reality is math can be hard, but lots of things are hard. You know, sports can be hard, lots of things are hard. And students can be given the confidence and the skills and the step-by-step whatever they need so that they can do the math. There are these certain cultural misunderstandings. I don't see them here in Ontario so much, but in parts of the US, there are what are called the math wars. There's many people who believe that students have to know the multiplication tables by heart and be able to recite them instantly. And if that's not happening, you know, you're a terrible math teacher and should be fired. That's the test that they understand. And I understand why they think that, because they went through a school where that was, you know, inculcated in them. But that's not math. That's knowing your multiplication tables. And it's great to know your multiplication tables. It helps you later do other things faster in your mind. It's good to work on figuring out why, because you're working on patterns. But that's not math. That's multiplication tables. Another problem teachers are facing is that often the parents cannot help. So I was lucky enough to have parents that are always making me think about mathematical things, I think, when I look back on it. But in many cases, parents cannot provide that guidance. So there's a lot of time there in which you're not being encouraged to think mathematically. Another issue here is that society doesn't want to invest in education. In fact, I'm going to make that red. That is the most important issue in my mind. People they know a lot about what makes education better, okay? Ask any millionaire what they would like their child to have, and they'll say, oh, I'd like to have a small classroom, and they'll put them in a private school with a little class. I'd like to have, wonderful resources. They'll put the kid in a private school with many things. I want to have field trips, and I want to have a beautiful, safe environment. If people have the money to do that, they give that to their children because they want it. There's a cultural problem that people don't want to spend that money on other people's kids. That's what I see as the fundamental difficulty with improving education. Nobody wants their taxes raised because they don't see investing in this future generation's education for the value that I see. We have just different values on what's important to spend your money on. Because of that, there's lots of big things you could do to make education better, which I won't propose because it's a different fantasy conversation. Instead, I can think about things on a smaller scale, incremental changes that are feasible, given that nobody wants to spend any money. So let me go back to the state of math education right now. As I said, this is sort of what you see in the classroom sequence of things. And it's important to understand why we have this set of classes. I showed you this picture earlier, this mind map with all these different fields of math. We've chosen this particular set. And to understand that, think of it in the bigger context of what happens in university education. If K through 12 can get you up to trigonometry and pre-calculus, then in your first year of university, you can take calculus. In your second year of university, you can take differential equations. And then you're ready for technical subjects. In your third and fourth, you can do applications of differential equations. So everything in that school, that K through 12, is actually driven by the need to get to differential equations. It's a branch of math that you may never have heard of, or at least not heard of the term, but it's what's driven your math curriculum. So differential equations are a kind of equation that describes how things change, how they move over time, or how they can spread over space. So if you're a chemist studying diffusion of things through something, or if you're an engineer looking at how heat flows through a piece of metal, if you're a epidemiologist and you're looking at how a certain amount of disease then spreads to another amount of disease, there are equations that express how things change as a function of the current state. If you're driving at a constant velocity, it's very simple. You know, at 10 miles an hour, for 1 hour, you go 10 miles. But if things are varying the forces, if you want to get a rocket on the moon, if you want to understand the complexities of weather, okay, so the reason why we're having this huge hurricane this week is because there's hot water that goes up, and if there are differential equations that explain that, meteorologists who understand them can do that. Many, many fields of science, engineering, social sciences, economics, rely on differential equations to express change, to be able to predict, control, understand dynamic systems. It's a crucial subject. You cannot be at the forefront of your field in any of those topics. You would not be a research chemist or physicist if you don't understand differential equations. So the entire school curriculum gets you ready to have 1 year of calculus, 1 year of differential equations, and then you can actually use them in your chemistry classes or your whatever other classes. And that's the constraint that makes the culture give us those classes on the left. What I would just say is that if we didn't need to get to differential equations, then you're free to take lots of other math. I don't want to say not to take math. I want to encourage you to take lots of math because it's so wonderful. But you don't have to take that particular math. You maybe could never take calculus or take calculus, you know, in your senior year of university. There's some beautiful branches of math that could be taught much sooner, that could be explained at some level in high school. So there's lots of different options. There's a societal problem of how do we tell a younger person that we're not going to put you on that track that gets you to differential equations. Instead, you're free to take those others. But now you're giving up the ability to be, you know, a research physicist because you haven't had calculus in your first year of college. It's a hard problem. I don't know how you solve that, but if you agree that certain people don't have to get to differential equations, they could take a lot of other math. We can free them up to take many other interesting things. How you judge who should do what is tricky. Anyway, but there's lots of things there that are fun that high school students could learn and enjoy, and that are beautiful, and that teach you more about math. Okay. So I think I'm at the point where I'm supposed to break, or just about to. So given all that background, I think we're going to have a 15-minute cookie and coffee break. And then we're going to come back, and I'll tell you some things that I think are good. I guess I have 1 minute. First of all, I'm going to talk about incremental changes, not big disruptive changes, just little things that are not expensive. I just want to point out, in the break, feel free to come up here and have a bite of bagel or look at the different objects I have on display. Many of these are things that students can build in a classroom, and after the break, I'll show you some examples of students doing that. Thank you. So what I want to do now is just sort of tell you, based on, again, my particular perspective of kind of the university level and classroom visits, just some ideas on how I see education, things you could do, and I've already shown you a couple of videos that what I consider math are, or what can be brought into math, are activities that are fun and creative, that get people excited, and that give you the opportunity to talk about math, to see patterns, to think about math. So I just have a whole bunch of things here, and I'll just blather on a little bit about each one, a certain amount. I'm going to begin with just kind of a list of observations. Starting with this famous quote. You can find many different versions and different attributions, but at least one internet web page says, the statement by Plutarch is that the way to think about the mind is not a vessel to fill, but as something you can ignite, wood that you're creating a fire. And I think that's a starting point for many educators. But I want to emphasize in the context of math education, it's not that your brain has an empty times table in there and your job is to kind of fill in, now you know 3 times 7, now you know 4 times 7. It's setting a fire that you're excited about multiplication, you're excited about math, so that you'll want to fill in that table. You want to understand those things. You want to learn a lot more. What I want to do is create an emotional connection to math. I want to get people excited about math. I want them to see the beauty and to enjoy the process of discovery, the challenge, and that's the direction that these different activities come from. A second observation is that math is beautiful. I mentioned before that there are people who say, "What a beautiful theorem! This is, one of the best theorems." There are people that go around writing books, collecting the most beautiful theorems, selected by their elegance, their beauty of the proofs, and part of what you learn, I think, in the undergraduate math career is an aesthetic. Good professors pass on the aesthetic. When they teach, they'll tell you, this is really beautiful. Can you see how I didn't have to use all that stuff? I only needed 3 simple things, and that was enough to prove this, or whatever makes it an elegant proof to a mathematician. And it's something that takes time to learn. It's something that's passed on in an individual way. Another observation is that language is everywhere, but math needs to be shown. This is actually one of Elizabeth's classrooms some years ago. It's highly decorated with mathematical things. Many of those things, most of those things, maybe all, are things that students created in activities in the classroom, then hung up to display. Sadly, the school does not allow hanging up things anymore. Since COVID, they've made it, illegal to have beautiful math on display to inspire children. A step in the wrong direction maybe can get repaired. But we have a room in each school called a library. We have public buildings called libraries. We have, museums that have quotes by scientists emblazed in stone on the wall. We have stone tablets, ways of representing language, quotes, famous authors. We don't have that for math enough. So I briefly mentioned that one of my projects was to create a museum of mathematics in New York City, kind of an institution for a place you can go for math, but that's not scalable to everywhere. We need more math on display, and by having students build things and put it in their school, or having people in public just create things that are geometric, it then shows people that, oh look, there are cool mathematical things to think about, to be impressed by. And it's therefore inspiring. It gets people to think, it gets people to talk to each other. Students who made one thing then tell students in another class, here's what I made, here's what it is, here's how it works, here's how we do it, and then they want to make another one, or a better one, a different one. It inspires you to think about these patterns and structures and explanations. Again, more pictures from Elizabeth's classroom. Here's the idea. We think this may be a Scandinavian quote somewhere from someone, but the idea is that school should be a model of ideal society. You should make it inviting, you should be beautiful, it should be safe, no one should be hungry, no one should be feeling any threatening. They want to feel that you can go there, and it's just a wonderful place. And having beautiful math thing as part of our mathematical culture is part of what I see that. The idea is that then, if students have seen this and grown up with this, when they leave school and they're out in the world, when things aren't as ideal as they could be, they now know it's possible to have a more ideal, and they'll work for it. They'll struggle, they'll argue for whatever political changes, etc. So schools should be as beautiful and mathy as possible, among other things. In this corner hanging up there on the top left, you may see and might immediately recognize a 4-dimensional hypercube built by this student. So another observation is that it's perfectly fine to show people things that they can't yet understand, that are not part of their grade level curriculum. This student just built a hypercube. It's a 3-dimensional projection of a 4-dimensional regular polytope. He doesn't understand all that, but he sees the structure. This particular structure is something that comes up in a lot of places. In the university level, you might study, computer networks that are organized according to this particular graphic arrangement. You'll show up in mathematical analysis of many things. It's just a fundamental structure that's universal. And he's already seen it. He has a mental model of it. In a later point in his life, when that comes up, he has a kind of an anchor. It's a familiar thing that then he can add to his knowledge too. It's just like you don't, like you can read a book to a student who doesn't understand everything. They can know that there's books there in the library that are not their level yet, but they can then aspire to it. They can be familiar with it, and they can have a head start when they are ready to get into it deeper. Another observation is that we can emphasize creativity. When you're teaching math, it should be taught as not a rote subject, but as a subject just full of challenges and problems and creative solutions. One of the sad stories I've heard variations of from many, many professional mathematicians is that they were given some homework problem in their K through 12 curriculum, and they came up with an interesting solution, and the teacher didn't get it. It was too creative. The teacher says, oh no, in the back of the book it says you have to do this, this, and this. That's their model for what the answer is, and they marked the student wrong when the student had a better answer. And we just need an awareness that in mathematics, especially when you're explaining things, there isn't just one answer. There can be many different answers, different perspectives, and seeing them all gives you a much richer picture. You're able to see things from different sides because it can be explained and understood in so many different ways. So we need to emphasize the creative solutions and acknowledge how wonderful that is. Another observation is that lifetime attitudes are set in school, particularly in the younger grades. These people are all joyous over having made these little versions of that hyperboloid I showed you the video. Especially in the youngest grades, people are most impressionable. So it's sort of sad to me that so many teachers in the younger grades will tell you that they're not really math people, that they don't get math. I've heard this from said teachers. We have this structural problem that the people going into education who are most comfortable with math, who like it the most, tend to go into the upper grades where they can teach more advanced courses that they find more interesting. The people who often self-select to teach the lower grades are often people, not often, or more often, people who don't like math and might be passing on attitudes about math to the people who are most impressionable. I don't know how to fix that. It's a generational problem. It's happened over generations for us to be where we are. And to fix it, I can imagine slowly increasing the comfort and the mathematical sophistication of elementary school teachers. But that is important to think about, that we ideally would have, mathematical minds teaching young people, and many would love to do it, but they can earn much more money being a lawyer or a doctor or something, so they choose not to be a teacher when they might be a wonderful teacher because of the current economics of education. Another thing to think about is how math builds confidence. When we make someone better at math, we're making them better in all their subjects and in all their life. People brand themselves, am I smart? I can do math, yes. Am I stupid because I can't do math? That's just a cultural issue, so that when we help someone learn math, not only do they bring in these problem-solving skills and tools that can help in all their other subjects' content, but we're also helping them emotionally feel like a stronger person capable of doing much more. Another important observation is that math can be a social activity. Humans are social animals. We love working together in groups. Some people's concept of math is that you're going to work on this particular sheet all by yourself, and you're doing math. It's much better to do math with friends, in a group, in a social setting. A lot of the activities that I do are group constructions, particularly because that creates a social dynamic. It creates conversations, creates memories and stories about how we built this thing together. It's an opportunity for people who understand one thing to explain it to another while they explain something back to the first group. So thinking of math socially is important. If your plan for math education is that every student will sit in front of a laptop and be tutored by an AI, that's a bad plan, okay? People are not going to learn, or almost all people are not going to learn math in that way. We want to make it social. Another thing to realize is that students can learn much more than what's in the curriculum. These students have each built, using a toy called Zone Tool, they've made some fairly complex polyhedra. There's icosahedra, dodecahedra, rhombic tricondahedron, I don't know, rhombic dodecahedron. There's a lot of shapes there. They know what those shapes are. We've talked about them. This was from a period when I'd come in every Friday and spend a couple of hours with Elizabeth's class. And just like kids learn dinosaurs, you show them a book of dinosaurs and they'll tell you about the Brontosaurus and the Tyrannosaurus and whatever elsesaurus. Those students can tell you exactly what they are. I built a dodecahedron that has an icosahedron inside it. They understand those things. They like them. They appreciate them. We can give students much more as a form of enrichment just because it's fun and interesting. And it turns out those shapes are useful. If later they're a crystallographer or a computer scientist or something, they'll want to know those shapes very, very well. But they are just beautiful, fun things to do that we can do. Another observation is that math can be done outdoors, like most of school. We had a talk here a few weeks ago about outdoor education, or last week. This is a professional development activity I was doing. This is in Central Park in New York City. A bunch of first-year teachers came together, and we built that structure. I think I have a close-up picture of it later. It's I think it's an expanded 600 cell. I have to see it, a close-up of it, but it's a thing made out of thousands of pieces that come together that represents a four-dimensional object's shadow in 3 dimensions. And it was a great, fun kind of team-building activity over 3 or 4 hours one afternoon outdoors. Another thing to think about is that large objects can be impressive. So this is a dome Elizabeth and I are sitting in, but it was built by, this was university students at Stony Brook. Large cardboard dome, pieces calculated and cut out on a laser cutter, and that they're glued together by the students. It's modular. You can take it apart, bring it outdoors, back indoors. When you make something big, you're conferring on it a kind of a stature. You're saying this is important. It's a giant monument. It's not just a little thing. You're making a public statement that I value this thing, so that other people will look at it with more intent, with more appreciation, and spend more time. So think about making things large. Another thing to think about is that hands-on activities are not just for little kids. So there are lots and lots of wonderful math manipulatives, you know, counting by 10 rods and things that are used in elementary grades. High school teachers tend not to do that. So this is a structure made of 12 playing cards, very hard to make. It looks simple when it's done. There's a regularity, a symmetry to it, but when you have just the pieces or the half done and it's a floppy thing, it's really confusing. The way to explain this to people so they can build it is to understand that there's 12 cards and they actually correspond to the 12 edges of a cube. It's an example of an isomorphism. I talked about the isomorphism between the counting with addition and the doubling with multiplication. This is isomorphic to a cube. If you have a mental model of a cube, and everyone does, you just connect up the pieces in groups of 3, like 3 edges meet at the corner of a cube, and that instruction helps you do it. But being able to see the importance of that parallelism and to think of it as a formal isomorphism is something that high school students can do to then build this. And when you design activities for the upper grades, you just have to make them more challenging, more interesting, you know, appropriate for that level. A fun thing about this is that these modules then stick together, so you can build like 3-dimensional lattices, and it's just kind of a fun thing in addition to being an elegant structure. What else can we say? I like to keep in mind that school is aimed towards differential equations, so that some of the activities that we do in high school are giving a sort of a foretaste of things that you might see later. So this is a catenary arch. On the blackboard in the background, you can see this is a level of high school seniors that we were doing this with. I was trying to explain some aspects of the catenary curve, how it's an exponential. It's similar to a parabola, but a parabola is polynomial. The exponential of the catenary has different asymptotic properties. There's a lot of mathematical things you can bring in while they're building this, so that when they later get to the point that they can see the differential equation of a catenary and understand it at greater depth, they already have a familiarity with the object. It's a known thing, in addition to being an absolutely beautiful shape. I just love the catenary. This is a professional development activity with a group of teachers in New York somewhere. We're building a big cardboard sculpture. And it's something which, again, I can design, I can show you how to use a laser cutter or whatever to create the pieces. I can teach you how to do it. And working with teachers, it now becomes one more tool in their kind of storehouse of things they can bring into the classroom. I'm not a classroom teacher, as I said. I don't know what's the right thing. But talking to the teachers, I know they like to bring in fun things. It's fun for them to do in this situation, but it's also one more thing that now they have available. So I'll show you our website in a minute. Elizabeth and I have created that has a whole bunch of activities, including cardboard constructions, that teachers can choose to use when they feel it helps them in their classroom. Here's an important point about technology. Educational technology is a huge issue. It's like a billion-dollar industry. Every kind of technology you can think of has been claimed at some point to be, what's going to save education. When I was a kid, we had film strips. Those are going to save education. When the radio came out, professors would give a lecture and the whole world can learn this course. Television was like that. In the last decade, YouTube videos, the Khan Academy says, if you just watch these videos, you will become, learn everything you need. The big money maker now, everyone is putting literally billions of dollars into education with AI. Every company in the world that does AI wants to get it into every classroom. They actually want to just get all your data so they can sell it, is my view. But they'll claim that they want to solve education by having your personalized tutor that understands you. Again and again and again, the use of technology as the fix for saving education has failed. And I think the reason is because the people who are proposing it are purely interested in selling that product if they can find someone gullible enough to buy it. They don't understand what education is, what actually happens in a classroom. So here, these students are building a sculpture. It's actually a larger version of this. These are elementary students. That one is bigger. It's held together with cable ties. It's a fun thing. It's kind of a beautiful thing. You can hang it up and display it. You can understand the patterns, and you can talk about pentagons and triangles and all kinds of geometry. And it's only possible to do this. I can make that for a couple of dollars because I have a laser cutter. The laser cutter is an enabling technology to make very accurate flat pieces inexpensively. So knowing that, I can design a way that it can be brought into the classroom. So there are uses of technology that allow you to do new things. But don't think that every new technology is like going to solve all of education, which is what the people selling that will tell you. And AI being the current big one that I recommend you be aware of. And I have one last observation on this list. This one just says that the content things I'm talking about is not most of education. It's the social things. I believe that what teachers are doing when they're dealing with the whole person, with the student who needs encouragement, with the student who's hungry, with the student who has family problems or abuse at home or whatever, when the teacher is being a role model and encouraging and figuring out who can be pushed a little harder and who just needs a little hint at that stage. Those are the aspects of teaching which I am no good at all. I know my limits. I'm good at making little mathematical things and popping in and having fun and leaving. Most of what teachers do that makes them such wonderful people are these social things, and the technology doesn't fix that. Having students sit in front of a laptop and they're going to learn is not what school should be, and it's not going to work. So I just want to sort of just put as a footnote to everything else I'm saying that I don't know how to fix those things other than to have real, wonderful, caring, intelligent teachers in the classroom. Okay, so in a couple of remaining minutes, I'm just going to show you some of the activities that I've been doing, Elizabeth and I have done as workshops, and as teacher events. I'll mix in some public sculptures and group assemblies, and I already showed you a couple of math videos, but I have a whole bunch of videos online that you can go to. I tend not to be I don't get millions of hits because the things that I present are things that I think is cool, and I'm not connecting to the generation that talks with videos. But I still think they're cool, and if you're interested in knowing more, you can look at them. So we have a website called makingmathvisible.com, and it has a little bit about sort of our teaching philosophy, but mostly it has a bunch of workshops, hands-on things. You can go there, and it has step-by-step instructions on how to teach these things, templates for printing things out, or what to cut out on a laser cutter if your school has a laser cutter. It's all free. It's all available. People around the world discover these things and use them. We get feedback from teachers who tell us it's wonderful. But it's just a small part of education, but it's the thing that I can do, so I do it. I'll first show you a couple of sculptures. This is at Duke University. This is big metal orbs built as a group construction. So I bring the pieces, I have people help me build it, it sort of becomes their sculpture. We talk informally about the math and the patterns and the symmetry and the polyhedra, etc. It goes up, and this is in the engineering building there. It becomes a large, permanent symbol of the beauty and the depth of mathematics. I've played a lot with 3D printing. It's enormously powerful for creating shapes that are too intricate to make by hand. It can make things very accurate, very beautiful. I have one model here, but I won't talk much about that. But that can be brought into the classroom, but it has to be done carefully, I think. The sweet spot for making large sculptures in terms of materials is wood. Metal sculptures are expensive to produce. Paper is kind of soft and floppy. Cardboard is pretty good. It'll last a while. But you can make plywood fairly inexpensively. It'll last basically forever. Cable ties is a great way to construct things because it adapts to whatever angles you have. So I design a lot of sculptures to be made with plywood and cable ties, like the blue one I showed. Here's one, I forget, in Michigan or someplace. Intricate, but a fun social activity for people to put together. This is the one I showed before in Central Park, a little closer look up. Here are some paper activities, very affordable. I brought one that's a solid color, but we have a whole series of ones online using different polygons that assemble. They're much trickier than they look, and yet they're very doable at the elementary grade. They're a challenge. You can first build them without color just to understand the geometric form, and then build them again with various coloring patterns, like use 5 colors, but always have no two of the same color touch themselves. And it becomes an extra puzzle with interesting solutions. So there's a whole series of paper constructions online. And halfway, it turns out, no matter what we build, halfway in the project, it is a hat. Again, social thing. These are easiest to build in pairs, 2 people working together, which just encourages the social aspect. Similarly, you can build things out of CDs very inexpensively. These are CDs and cable ties. This is the structure of a soccer ball. In class, we'll call it a truncated icosahedron and explain how it relates to an icosahedron and have people draw it first to really understand it before they build it. Again, also a social activity because people can be working on all different sides of it at once. I showed some Zoom Tool earlier. Zoom Tool is a commercial, plastic construction toy designed by an architect in the 1970s. It happens to have just the right lengths and angles to make an enormous range of really interesting mathematical structures. So I like to use it, and students can build all kinds of cool things. There's something called the 120 cell, one of my favorite 4-dimensional objects, and has a cool shadow, just demonstrating that. This is a sculpture made of pencils. And this is one that I built as an art piece, but the construction of it is something that you can do at a young age. What's interesting, what makes it mentally challenging, is that the pencils go in 4 directions. You may be used to sort of X, Y, Z axes, 3 orthogonal directions. Here are 4 symmetrical directions. They're the directions of the diagonals of a cube. So a cube has 8 corners. If you go from one to the opposite, you have 4 lines in space that form a different kind of coordinate system, and the pencils go in that direction. It's something of an expansion of your mind to get familiar with it and to realize how regular and beautiful it can be. Here's a version of this that I did in Korea 10 years more ago, but hundreds and hundreds were built out of chopsticks that day. We show the video of this activity with skewer hyperboloids. So this is something where it's wonderful that young women have the advantage of understanding rubber bands in depth. These are little ponytail rubber bands, and can really shine in building it faster than the boys. This is a teacher's workshop, I think at an OAME conference a few years back, Elizabeth and I did. The cool thing is, after you show people how to make it out of the little sticks, you just hand them a pile of big ones and a bag of rubber bands and sit down, and they take care of it from there on. And again, you can combine them in different ways. This I showed you before was the playing card constructions, and there's several of them on our website. String rings are kind of fun. This is just a laser cut ring with some notches, and they're numbered, and you connect from, keep adding 10. You go from number 3 to 13 to 23 to make one kind of ring. But if you switch from addition to multiplication, I think I brought one you can see on the floor down here. I'll hold it up. This is what you get if you double. So if the holes are labeled 0, 1, 2, 3, 4, 5, starting with 0, and you connect hole I to hole 2 times I, so 7 goes to 14, 8 goes to 16, etc., it turns out you make a cardioid, a wonderful thing. If you have energy and interest and want to do a mathematical experiment, you can say, well, what happens if I go from hole I to hole 3 times I, or hole 4 times I? And I will leave that as an exercise, but you'll get a nephroid in case you're curious. Puzzles, this is a classic wooden puzzle called Soma. Students are building this out of cubes, but then if you have them build it large out of boxes with packing tape, they love playing with boxes and packing tape. We make this big puzzle, and you give them a sheet of all different things they can build with it, and they will build, they will love it. You can do one each day at the start of your classroom, whatever, and the bigger the boxes, the better. This is actually, I think, in Hepworth, a large cardboard construction. Cut out the pieces. The students first clamp them together with clamps, and then after it's all built, one at a time, take off the clamp, brush in a little glue, put the clamp back on until the glue dries, and then after an hour or less, you can take out the clamps, and the sculpture is there. Just a larger, more complex one at a university level. There's actually two. It's a left hand and a right hand form, which just adds to the mental challenge. There's many variations on these on our websites. Domes, I'll just run through quickly because I'm going low on time, but people love domes. There's Elizabeth and half her class inside a Zoom tool dome. With a laser cutter, it's very easy to cut out wooden pieces and little connectors, build something interesting like that. And I showed you a picture of this before, of a larger one. Big enough for a whole lot of people to sit inside of, and structurally quite strong out of cardboard. And catenary, we saw a little bit of, we do a version of this first in paper, then in cardboard, and then in wood. This is a rhombic tricontahedron puzzle. Again, a geometric challenge. It's like cubes, but they're skewed. It gets your mind thinking. These I have some of on the table, are things that you can make with popsicle sticks, much more challenging than it looks, good for high schoolers. And I showed you this sculpture before, laser cut wooden pieces with cable ties. We have some variations on this. And I think I'm going to leave you with this. So you could read some student comments. As I said, I am not a professional who can assess these things and go in and give a test and see, does your long division score increase after doing these activities? I believe they have enormous worth in helping you think like a mathematician. The only feedback I have is that I can tell you students love this. If the goal is to first make an emotional connection to math, people like math so they'll go on and do the work. I think this is the kind of proof that shows that we are making that emotional connection. And I think that's essential in then getting people to go on and put more time and energy and value in math. So I will stop here and be very happy to have questions.